All right, we're starting to record, so why don't we get started? And I just got kicked off, I think. Did I? No.
No.
All
No,
right.
we can see it.
Something weird just happened. Yeah. All right. We're good? You guys can see my slides?
Yeah.
All right. Yes? Okay. Great. So why don't we get started? So where we ended last time was one slide back. Well, I don't have to go back, but we were determining pH, right? I would say, like, here's the concentration hydronium, find the pH, or here's the pH, tell me the concentration of hydronium, right? Now what we're going to get into is a little bit more what happens in real life. How do I determine the pH of when I mix a strong acid with water, right? How do I determine what the pH will be? A more complicated, not that much more complicated question, but what happens if I take a weak acid and add it to water, right? Can I predict what the pH is going to be? And that's what we're going to focus on today. Like I said, I think with our time constraints today, I don't think we're going to get to polyprotic acids. Like I said, yeah, like I'm saying, I think today is just going to be strong and weak. So we'll start with the easier one first, which is with strong acids, right? So I gave you a list on Wednesday, I believe, or maybe it was week before, on 4 strong acids that you need to memorize. And then we said everything else is going to be a weak acid as long as it's an acid that I tell you, right? Usually on an exam or a quiz, mostly of the time I'll tell you weak or strong. But we're going to start to learn by the end of the chapter, there's going to be 2 other ways to judge if something is strong or weak. The first one is going to be Ka, and then we'll talk about the other one later, but it's structure. You can sometimes predict if it's weak or strong. But one aspect of strong acids is that their Kas are very large, right? So a Ka is just going to be another one of those equilibrium constants that get a special subscript, right? We've already seen Kc, we've seen Kw, we've seen Kp, right? The subscript is just telling you what you're dealing with. Ka means I'm dealing with an acid. Eventually, we'll get to bases and we'll deal with Kb, which will be the equilibrium constant for a base. So if I was going to write out a Ka expression, so I have a generic acid reaction here. There's a strong acid, HA, maybe it's hydrochloric acid, right? It's an acid, it's reacting with water, so water will be the base. Water will accept that proton, right? Because it's the base, the HA is the acid, so it's donating the proton. We'll end up with hydronium and our conjugate base. As with all Ks, we have our products, H3O plus and the conjugate base, over my reactants, and we know we don't include pure liquids or pure solids in our K expression. So the generic Ka expression looks like this. It's still products over reactants. The nice thing about this is it pretty much always keeps this form. The only thing you really need to update is what's the actual identity of the conjugate base? What's the actual protonated acid? So something like hydrochloric acid. Chloride would be the conjugate base, and HCl would be the protonated acid. So not too bad. Just to give you a sense of when I'm saying like how big a Ka is. So something like hydrochloric acid, which is a strong acid, right? That Ka is approximately 1 million. So it's very large, right? That's what I mean by very large. To put that into perspective, what does that mean? The Ka is roughly, I can't write out the whole number, it's not enough space, but 1 million to 1. That means for every 1 million products, so 1 million hydroniums or 1 million conjugate base, you'll only find 1 protonated acid floating around. So it's saying basically 99.999, don't quote me on that one, % is in the product. So it's basically effectively saying 100% or approximately 100% of the reaction goes to completion. And so that's why for strong acids, we only usually draw a unidirectional arrow and not an equilibrium. Though if you're being super specific, yes, there is an equilibrium. but it's convention to draw it as a unidirectional arrow. So what I want to do on this slide is I'm going to walk you through how to attack a problem like this. And then on the next problem, I'm going to hand it over to all of you. So I'm going to teach you a way to do this. This is kind of like the long way. The book does not do this. I've never seen another book do this. I'm going to apply an ice table to this problem. It's not a real ice table. I'll call it a quote unquote ice table, and you'll see what I mean in a minute. So let's read through the problem and then talk about the steps of how we want to attack it. So it says, what is the pH of a 0.025 molar solution of nitric acid? So two things. One, we need to know that nitric acid is strong. B, we could also, that could be our memorization, A, we memorized it, or B, we know we're dealing with strong acids in this section. So almost always for a pH type question, not always, but almost always, the way you want to start is you got to write down the chemical reaction that's happening, and it sometimes gives you that perspective like, okay, what am I looking at here? So if I was going to write out the chemical reaction for nitric acid reacting with water, so we have our nitric acid. It's reacting with water. Because this is a strong acid, I'll use a unidirectional arrow, and that's why it's kind of weird to use an ice table for this, but you'll see what I mean in a minute. If I'm predicting my products, I know I have my acid. It will donate the hydrogen to the base, so I'll be left over with nitrate. And then I have my protonated water, which is hydronium. Let me clean up my the left-hand side of it, right? And so we start off with our chemical reaction. What are we looking at? Now we can set up what I'm going to call an ice table. It really isn't, this is not the way you would typically solve it, but I think it's a good visualization. And then what I'm going to teach you afterwards is the quick way to do it. So this is like the visualization way, or if you get stuck, you can always fall back on it. So if I was going through, like any other ice table I'd be setting up, I start with my initial column or initial row. So I know I started with 0.025 molar nitric acid. This is a little unusual. I tried a bunch of different ways to teach this, but I think the best way to do it is just say there's a lot of water. So we know water doesn't show up in the K expression because it's a pure liquid, and we said it's based on its density, right? So its concentration never really changes. And if you do the math out, the amount of water is 55 molar. So that's a lot. And you're comparing that to 0.025 molar. We're basically saying there's so much water, I'm not even gonna care if some of it gets consumed. Effectively, like it's still gonna be 55 molar. Right, so I'm just going to call it a lot. I read through the rest of the problem and I recognize that it didn't say anything about nitrate. So my nitrate concentration is 0. And so in real life, when you take nitric acid and you bubble it through water, so technically it's a gas, I think. Yeah, it is. And you bubble it through water, right? As soon as it hits the water, things start reacting, right? What we're going to do is this is more like a thought experiment. We pretend like we can pause time. So it's like we added that HNO3, we pause time so the water can't react with it. So that's kind of what our initial conditions are going to be. What does it look like if as soon as I mix them, I pause time? As soon as I mix them, well, nothing reacted. So my concentration remains unchanged. I still got a lot of water. I didn't add any nitrate, so it's 0. The last thing I want to mention is going to be the concentration of hydronium. And I'm going to call it approximately 0. Does anyone have maybe wager, just an idea, maybe just throw it out there, see what happens. Why do you think I'm saying approximately 0 hydronium is the concentration, 0 molar? So Jess, maybe you just wager a guess. Why do you think approximately instead of 0? And if you don't know, it's always fine to say you don't know.
Sorry, I don't know.
Oh, that's totally fine. Anyone else want to jump on it? Just an idea why I'm saying approximately 0?
Is it?
Does it have to? Oh, sorry, go ahead.
You go ahead. You're probably right.
I am just taking a wild guess. Does it just have to do with the fact that only approximately 100% of the products are made?
So the thing is, we haven't, so imagine this, right? We said actually, in this case, there's actually no reaction. I'm just trying to describe how does my starting, like if I had a beaker, filled with water and then nitric acid, but I don't allow them to react, we're just describing what that looks like. So technically there's no reaction yet. So it makes sense they had the zero nitrate, but I didn't see, because everything pauses on my screen. So Elena, you mentioned that. I didn't hear the first voice. I didn't hear who that was. But what was the other student who was saying maybe wagering a guess?
I maybe it has to do that Ka is so large, but that's after it reacts. So I don't know.
That's part. I love how you just corrected that. You said because that's after it reacted. Great. So I like where everyone's thinking. It's good. They're actually, these are really good answers. But what we're actually, the reason why I'm saying approximately zero, remember pure water can react with itself. And so even when you pull it off the shelf, there's already a small amount of hydronium and hydroxide. And at 25 degrees Celsius, right, we said those concentrations are 10 to the -7. So they're very small, right? So technically, the concentration here is 10 to the -7th molar, because before the nitric acid even reacts with the water has already reacted with itself, because at equilibrium, the water already has the hydronium. Why can I say it's approximately zero, though? Let me show you, right? So the reason why I say approximately zero is because we're going to compare the concentration of hydronium at equilibrium to that starting amount of nitric acid, right? So the nitric acid, the concentration we're dealing with is on the order of magnitude of like 3 decimal places past the zero, or sorry, 3 places past the decimal place. 10 to the -7th is that small. It is so much smaller than the 0.025, it's effectively zero. It's like the idea of taking the number 1 million and subtracting the number 1 from it. You get 9,999, 900,009, whatever it is, 999,999, right? It's effectively still a million. That's why we're going to call it water, the hydronium concentration to start with is so little, it's zero. All right. So I like how everyone was thinking about that. It means we have our head in the game. And so this next step, I'm going to treat this like a regular ice table. I'll get rid of that approximate sign so it's a little bit more clear, right? Our products have zero concentration, so there's no way the reverse reaction can even happen. So I know the forward reaction must happen to produce products. And I'll give you a little hint. The molar ratio is always 1 to 1 to 1 for acid ice tables, or acid plus water. That's the nice thing. So you can always predict what the products are going to be. You can always predict what your change row is going to be. Everything is a 1 to 1 to 1 to 1 molar ratio. So a little hint, a little helpful hint. The thing here is, unlike regular ice tables when we need to solve for X, right? We're saying everything is effectively going to products, approximately 100%, 99.9999, I think, percent. That many nines, definitely 99.99. What that tells me then, if everything is going to products, that means I'm going to have no nitric acid left over. So my X must be equal to the concentration that nitric acid started at. So when I add up I and C, I end up with 0. So if I go through and replace all my X's with that 0.025, I'm going to end up with, well, a lot minus something that's minuscule. I still have a lot of water left. The nitrate, 0 plus 0.025 is 0.025. 0 plus 0, yeah, you guys got that? right? So we have our equilibrium concentrations. So effectively, you know, all of our nitric acid is now in the products. We just need to recognize what we're solving for. pH, well, it's gonna be based on the hydronium concentration. Because if we remember, pH equals the negative log concentration of hydronium. If I plug that in, I forgot off the top of my head what the number is. I think it's 1.6. And it is 1.6. And specifically 1.60, because remember, we wanted to keep track of our sig figs. I got 2 sig fig in the concentration of nitric acid. And remember our sig fig rules for log. We have 2 sig fig in our pH, despite having 3 numbers, right? That 1 in front of the decimal place in my pH, right? That's a placeholder. It's just telling me what order of magnitude. So we're in good shape. So what I just showed you there is I wouldn't ever recommend doing this out on a quiz like this because it takes too darn long. I'm going to teach you a quick way to do it. This way is not shown in the book, but I think it shows you exactly what's happening step by step. Let me show you the quick way. Right, so we wrote out our balanced chemical reaction. We have it's going to 100% completion, just like what we saw when we did it out slowly. For strong acids and strong bases, or for strong acids, let's keep it simple right now. The starting concentration of the strong acid will always equal the final concentration of hydronium. So in that case, really quick right off the bat, I recognize nitric acid is strong. I look at its concentration. I recognize that will be also the final concentration of hydronium when equilibrium is achieved. And then you just dump it into the equation and you're immediately done. So it's much faster to do it that way. The only reason I did that quote unquote ice table was to illustrate why the concentration of nitric acid to start with always equals the concentration of hydronium you end with. So any questions on that for clarification? Oh, sorry, I can't also see. Yeah, Gianna.
That's only for strong acids?
It is only for strong acids. Weak acids, which we'll get to in like 2 more slides, we're gonna have to do an ice table, but it will be a traditional ice table and you have to do the whole thing.
For a quiz or exam, for the work that we have to show, can we just show that bottom line? And
Yep,
like,
I'm fine with that. That is fine with me. And in fact, I'd encourage it because it saves a lot of time. So as long as you're comfortable with it. Everyone else set? Great. So this one's a little bit more tricky. I'm going to give you about 2 minutes to do this. Apply the same assumption. You can use an ice table if you want. My last class tried that. It took a long time to do because it takes a lot to write out. But apply a similar assumption that we did with strong acid. Sodium hydroxide is a strong base. We're going to apply a similar rule. The initial concentration of sodium hydroxide will equal the hydroxide concentration once everything's said and done, or the final concentration of hydroxide. So I'm going to give you guys 2 minutes to go at this one. Or maybe we'll try a minute first, and we'll see if we get answers. If not, we'll go to 2. All right, does anyone have an answer yet?
I got 12.4.
Yep, it is. It's 12.4. And if we go through it real quick, right, and there's a couple of things that we recognize. So we know the concentration that we started with NaOH has to be equal to the concentration of hydroxide final. So if I know the concentration of hydroxide and I have my Kw value, I immediately can solve for my, oops, let me do a different color, right? I can immediately solve for my hydronium. And if we, again, we recognize pH is the negative log of hydronium concentration, right? So we make our connection. I plug in my numbers. Oops, we got to solve for, I'll do the work down here. I'm going a little quick, right? But we know that hydronium is going to equal the 1.0 times 10 to the negative 14th divided by the concentration of hydroxide, which is 0.025. So we do that out, 1.0 times 10 to the negative 14 divided by the 0.025. I get 4.0 times 10 to the negative 13th. If I put that number in, right, I run out of space. I'll make it equal up here, but we get our 12.40. So I think it's like 12.398 or something like that. Then you're rounding to 2 sig fig because I got 2 sig fig here and then 2 sig fig in my final answer. So good, I'm glad. That was a really quick take on that. So hopefully people are starting to get a better feeling for these problems. I like this chapter a lot, not because I like acid-base chemistry, because it's kind of boring, but the types of problems in this are really good critical thinking skills, because it's not always obvious to go, to take what you have, what you start with, and get to where you're going. There's going to be multiple paths you can take. Sometimes there's only one, but you got to figure your way through it. And so there's our summary slide, exactly what we just wrote out. And that's it for determining pH for strong acids and strong bases. It's pretty straightforward on that. So we got about 18 more minutes. So we'll probably get through definitely the first problem. We might stop at setting up the next problem, but we'll see. I'd rather go a little slower and have everyone understand than rush through stuff. So let's talk a little bit about, actually, before we even start, anything on that last slide that we were talking about? Any questions on this? All right. So for weak acids, right? Instead of having very large KAs, KAs are going to be smaller. And typically, they're actually usually less than 1 for most acids. So you can see why there's a huge difference between something like 1,000,000 and something that might be 10 to the negative 3rd, right? You're talking about 9 orders of magnitude, which is enormous. When we write out the chemical equation for a generic weak acid reacting with water, right? HA, generic weak acid, it's going to donate its proton to water, forming hydronium in the conjugate base. The only major difference that we can see in the way the equation is set up is that we use the double-headed equilibrium arrow for weak acids because, like our definition was, it's only going to partially dissociate. And we'll see probably on that Patriots Day lecture, acetic acid, which can still burn you, only dissociates to about 4%. So you're talking about 100 versus 4%. A nice thing is, because in the same setup, the generic expression, the Ka is identical. At least the expression is identical to a strong acid, right? The only thing that you're really going to swap out will be whatever the conjugate base is and whatever the protonated acid is. So let's do this. I'm going to walk you through this one. I've already typed out the answer. So this is more just going to be like setting it up, following it through. I would not try to keep up trying to write everything down as I'm talking right now. If you want it for your notes, maybe, when I post it to YouTube tonight or tomorrow morning, maybe go back and fill it in because it will be a little bit quick, but I promise you, we will start, hopefully we'll get through it in like 2 minutes, and then that gives us enough time to actually do a real problem together. Not that this isn't a real problem, just a different type of problem. So if we read through this, it says the pH of a hydrofluoric acid solution, so the pH is 2.036, the concentration of HF is 0.25. It's asking, so it's plural, it says values. I used to have two things to solve for. It's typo. But what is the value of Ka for hydrofluoric acid? So I removed, there's two things to solve for. That's why it's plural, but I've switched it to one. So we're dealing with weak acids. So we write out our balanced chemical reaction of HF reacting with water, right? And the only difference from the last time we did it with the strong acids is we have the equilibrium arrow. For weak acids, though, we cannot make that assumption that the concentration of HF will equal the concentration of hydronium. Why? Well, because only some of that HF will actually convert into hydronium and fluoride, somewhere in the order of magnitude of 4% and lower, right? So if we set up our ice table like we normally would, our change in our equilibrium, right? We put in our starting values. There's my starting concentration, approximately 0 hydronium and 0 fluoride. Nothing's on the product side, so it has to be going forward. And then we have our equilibrium values. Just like we would with any other ice table, we can use our K expression. Oops, I guess I didn't write that down, so let me write that down. We have our K expression. We know that's going to be hydronium times fluoride over HF, right? I'm solving for Ka, and so that means I need to know all of those values, right? Something that's a little bit different. This is what I mean, like the critical thinking of these type problems. Usually I'd be kind of dead in the water here because I don't know my K and I don't know X. And X is, if I plugged everything in, right? What I have now is an equation. If I just look at the right-hand side, I have two unknowns, X and Ka. That is not possible to solve. So I'm going to have to find another way to solve. Well, what additional information do I have that I usually don't have in these types of problems? I have the pH. From pH, right, I can calculate, let me just do that here. From the pH, I can back calculate the concentration of hydronium. How? Right? If I rearrange that equation, hydronium is going to be equal 10 to the negative pH. Well, if I take a look, those are my unknowns, but if I take a look, I have my concentration of hydronium. It's X. That's what I'm solving for. The only other thing I would need is pH, and I got it. So let me show you on the next slide what I mean by that. Right? So if we know that the concentration of hydronium is equal to X, right? That's what I have here. X equals the concentration of hydronium. I rearrange that pH equation. I immediately solve for X. Without having to do any more work I can just dump in X into these equations. There's my Ka, H30 plus, and F, both equal to X. I already solved for it. HF is equal to the starting concentration minus X, right? And then I get my concentration of HF. Plug it in, it's plug and chug. We got our Ka. And what we can see here, this is kind of why we did this problem in a little bit different way, because we're solving for K this time. See how much smaller that is, compared. So HF, which is 10 to the negative fourth, compared to HCl, which is 10 to the positive sixth, just to give you a sense of how much these Ks can change. So hopefully that wasn't too bad, right? This was basically a problem similar to things we've seen in chapter 15. The only new aspect was like that critical thinking. Well, I'm stuck. Two unknowns, one equation, I'm dead in the water. Wait, I have additional information. I have the pH. From pH comes hydronium concentration. Hydronium equals X. Boom, I'm done, right? So we have 10 minutes. I don't think we'll get through it because I think this problem took about 20 minutes in my last class to solve. But what I would like to do is at least set it up. We'll see where we can get in about 10 minutes. And if we don't, what we'll do is next Wednesday, because remember, we're not going to meet on Monday because of Patriots Day. We'll just pick up here next Wednesday. So what I'm going to do, though, is leave a lot of this up to you. And this is why it's going to take probably 20 minutes, because I could get this done, once, and not just me, I'm saying once you guys get fluent with this, you'll get this done in minutes. What I want you to do, let's read through the problem, and then I'm going to give you prompts on what I want you to do, right, on how to solve for this. So it says calculate the pH of a 0.1 molar solution of hydrogen cyanide, right, so a hydrocyanic acid. It's at 25 degrees C, and it gives me the Ka. So I'm going to give you a stepwise procedure on how to start. So I'm going to give you a minute. I want you to write out the chemical reaction where hydrogen cyanide reacts with water, and then you have to predict the products. So I'll give you, a minute to do that, or less than a minute. Let's go 45 seconds. All right, that's probably enough time. It's not 45 seconds, but Emma, do you have a chemical reaction for me?
Yeah, I got, should I say the reactants too?
Yeah, go for it.
HCN aqueous plus H2O liquid,
Mm-hmm.
and then the sign that,
Yeah.
yeah.
Double header.
H3O plus aqueous plus CN minus aqueous.
Exactly. So I'm leaving out because I realized there's a lot of stuff on the screen. I like how you gave me the states of matter, and on quizzes and stuff, definitely do that. Well, actually, you know what? Let's be right. Usually I try to do it to like not crowd up the screen, but let's do it right. Good. All right. So I'm going to leave this up to everyone now. So thank you on that one, Emma. Yeah, Emma, I did ask you. All right, so the next step, I want everyone to do this. Fill in the entire ice table, right? I'm not looking for numbers, you're gonna have X's in there, but I want you to fill in this entire ice table, given the information you have. So I'll give you about a minute and a half, 2 minutes to go for that. In about a minute. Let me just see, does anyone have a completed table they'd like to share instead of me cold calling? All right, let me try this. Hannah, do you have even at least the I column or I row done?
Yeah, I can try.
Yeah, I mean, trying is all I'm asking. So, yeah, what do you have going across?
For the HCN, I wrote 0.1.
Yep, I agree.
And for the H2O, I just kind of wrote a lot because that was what we wrote in the
Oh,
last.
yeah, you're right. No, it's actually really good. I forgot. Thanks. No, it's a really great assumption. You're right. I didn't tell you that, but that's a great assumption. We do have a lot. And instead of me writing a lot, usually I just put a line. I just did that, so, but yeah. So great, awesome.
And then for both of the H3O and the cyanide or CN, I wrote 0 and 0. And then
I agree. And so the only thing I would kind of say, usually I put approximately 0, but for this, I'll take 0. That's fine. Good.
For the C, I did minus 0.1 on the reactant side, plus 0.1 on the product side.
Yep, so that would work if it were strong, but we're dealing with the weak acid on this one. So for
Oh.
this one, what we actually need to do is actually do the traditional ice table. There does need to be an X. So if hydrogen cyanide were strong, you would be 100% correct. But in this case, we actually have to do a normal ice table because it's only going to be a small amount of X that actually dissociates.
Okay, so then the bottom would be 0.1 minus X, and
Yep.
then the thing, yeah, and then plus X plus X. So just X.
Exactly. Great. Awesome. All right. So I think we still got 5 minutes. We actually might be able to get through this. I think we might be in good shape. So the next thing, I'll do this one. Actually, I'm going to have to walk. Actually, we have 5 minutes, so I will walk you through this. So that's all I want right now in terms of like input, because the next part is kind of brand new. So we kind of need to walk through it slow. So just like any other ice table, what we would usually do here is recognize that we need to write a new equation. This K, instead of KC, it'll be KA, right? Where we have our products, which would be hydronium and cyanide all over HCN. And so if once we have that done, right, what we could do, I think I actually have this on the next slide, so let me go there. Right, so there's all the table we wrote in, there's our Ka, right? And so all I did here is plug in all our values into Ka. I went ahead, when we look here, I've already multiplied the concentrations of hydronium and cyanide together. Both were X, so it becomes X squared. And then we have the concentration of hydrogen cyanide, which was the 0.1 minus X. And then the Ka was given to us in the problem. So here, right, this looks pretty normal to us. Usually what we would do now is dump it into the quadratic equation, right? And actually the thing is, it will always work at this point. Dump it in the quadratic equation, you'll get the correct answer. However, part of this course is quantitative analysis. So what I'm going to have just for the first quiz, I'm going to require you to do this new technique to practice it. But for the final or anything like that, I will allow you to use the quadratic equation if you want. So what I'm going, actually, no, we have 3 minutes. We can probably finish this off. What we're going to practice now is making assumptions. And I'm going to require you to write out literally on a quiz the word assumption. And now we're going to assume that 0.1, oops, that's not the way I wanted to write it, that X is a lot smaller than 0.10. So when it was a strong acid, X actually would equal 0.1 in this case. But it's a weak acid. We're saying a tiny bit of it is actually going to form hydronium. And so if X is super small compared to 0.01, right, that's like that 1 million example I gave you before. If you have a million and you only subtract something small from it, 999,999 is approximately a million. That's a reasonable assumption to make. So what we'll do with our assumption of X being so tiny, what we're effectively saying is, come on, go, right? That if I subtract a teeny tiny number from 0.1, the final answer will be 0.1. And so that's what I have at the top up here, right? If that is effectively 0.1, I can rewrite the equation to look like this. Look how much easier this is. Instead of doing the quadratic equation, it basically becomes a simple algebra problem. Multiply both sides by 0.1, take the square root, and then you find out that X is going to be equal to 1.2 times 10 to the negative fifth. So the thing is, remember, we're making an assumption. We're going to have to check that assumption to make sure it's correct. Because if it's not, then the assumption fails and that doesn't mean anything. Why even do the problem if you made a terrible assumption? How do I check my assumption? Well, this was my assumption. How do I check it? I'll take the 0.1 and I'll subtract my X, which is 0.0000112. I do that math out. So I do the 0.1 minus 0.000012. I get 0.009998. we need to remember our old, we don't usually use subtraction rules that often with significant figures, but whatever number has the least amount of decimal places is the new, oop, I screwed up that number. That's why. It should be, oh, I messed up writing the number. Sorry guys, wasting time. I wrote that wrong. 0.09998, whatever. That's all I care about. So I do the subtraction, I apply sig fig, well that will round that number up. That rounds to 0.01. That means my assumption was correct. So I know that was kind of quick and we're out of time. I just want to show you one thing real quick before I let you go. Right, we'll do more checking assumptions. So if that was a little too fast, we will do it again. But we need to write our assumption and check our assumption. Our assumption held, so that means my x is good to go. All I need to do is dump my x into my pH equation. I go through, I get a pH of 4.92. What I always want to ask myself, does the number make sense? And it does. Why? Because I had a weak acid, I better have an acidic pH, it's less than 7. I'm good to go because less than 7. And the last thing I want to say, and it's only just literally just a line, and then I'll let you guys go. If you went through and did this with the quadratic equation, you would get the exact same number of 4.92. So that's what I'm saying. Making assumption is a good math skill to have. I'm going to require it on the quiz, but for the final or any exams like that, you can use the quadratic. All right. So we're 1 minute over already. But if you have no questions, you're free to go. If you do have questions, I'll stick around for a little bit and then answer those. So you're all set to go.